All right, hello everybody. This is the very first lesson of Unit 2 for AP Chemistry, and we are going over types of chemical bonds. Today's understanding is that atoms or ions bond due to interactions between them, forming molecules. So today's learning objective, you should be able to explain the relationship between the type of bonding and the properties of the elements participating in that bond. When we talk about types of bonding, there are two umbrella terms that are really important to know. The first is intramolecular forces. That is forces that are occurring between atoms within a compound or molecule. And then we have intermolecular forces, which is happening between those molecules. So for example, if we had a sample of carbon dioxide, the intramolecular forces are the double covalent bonds that exist between the carbon and the oxygen atoms. The intermolecular force is the force of attraction between one carbon dioxide molecule and another. So for Unit 2, we are going to be focusing on the intramolecular forces, and then when we move on to Unit 3, we're going to be focusing on the intermolecular forces. The strongest of the intramolecular forces is going to be a covalent network solid. This is just essentially a giant covalent molecule. So all of the atoms within this solid are all connected by covalent bonds. Then we have an ionic bond, also a very strong intramolecular force. That is when you have a metal and a non-metal, cation and anion, that are attracted through electrostatic forces. Then we have metallic bonding, that is between different metals, and they are connected by a sea of delocalized electrons. And then the weakest of the intramolecular forces is going to be a covalent bond, that is between nonmetals, and that is when the electrons are shared between the atoms. So remember, ionic bonds are formed when electrons are transferred from one atom to another atom. And when it does that, it creates a positive cation and a negative anion. And those oppositely charged ions are then held together by electrostatic attraction. So for example, if we're talking about sodium and chlorine, we know sodium has one valence electron, and we know chlorine has 7 valence electrons. So when these two atoms are near each other, in order to gain stability, sodium will donate its one valence electron to chlorine, and now they both have a stable octet. That means that sodium just lost an electron, so it has one extra proton, and chlorine just gained an electron, so it has one extra negative charge. So now that they are oppositely charged, they are attracted to each other by that electrostatic attraction. Then we have covalent bonding, which is formed when atoms share pairs of electrons to achieve that same stability. These can be polar or nonpolar depending on the electronegativity differences, and some common covalent molecules would be like water or carbon dioxide. Then we have metallic bonding. That's going to be found in metals, obviously. Positive metal cations are essentially going to create this lattice structure that are surrounded by a sea of delocalized electrons that are going to move freely throughout all of those cations. So what do I mean by that? Let's look at aluminum. So if we were to form an aluminum metal and we were looking at the particle level of our aluminum atoms, what would happen if they were all bonded metallically is the aluminums would form cations. So we know aluminums have 3 valence electrons. So when they would become ions, they would lose those 3 valence electrons and they would become aluminum 3+. So if all of these atoms become ions of 3+, that means it lost 3 electrons. So now in this very small sample, we have 12 electrons moving freely through all of those cations. That's the sea of delocalized electrons. And then we have covalent network solids, which is a special type of covalent bonding where atoms are bonded in a giant repeating 3D lattice of covalent bonds. and it creates a very strong and hard material with very high melting points. So let's start off with the strongest of the intramolecular forces, which are the covalent network solids. So these are going to be atoms that are held together by covalent bonds. It's essentially a giant covalent molecule. These covalent network solids have very high melting points. It's the highest melting point of all of the types of substances that we're going to be looking at. And it does not conduct electricity because those electrons are localized, meaning they don't move, they stay with the atom. And common covalent network solids that are assessed on AP chemistry are going to be diamond, which are just carbons that have 4 single bonds. So it looks kind of like this. Every single carbon in a diamond is bonded 4 times to neighboring carbons. Then we have graphite, which is again only carbon, but the carbon is sp2 hybridized, which means it is trigonal planar, so it's 2 single bonds and a double bond. So this blue structure is a very quick drawing of graphite. You can see that each carbon has 3 bonding sites, so it forms an sp2 hybridized carbon, which means the molecular shape is going to be trigonal planar. So when we're looking at graphite, it is on the same plane, whereas when we're looking at a diamond, the carbons are sp3 hybridized, which is tetrahedral. So a diamond would be a 3D macromolecule essentially, where graphite would be all on the same plane. And then 2 other covalent network molecules that are on AP chemistry a lot are silicon dioxide, which is SiO2, and silicon carbide, which is SiC. I strongly recommend memorizing those because they come up a lot in multiple choice questions. So if it's asking for which of the following is going to have the highest melting point, then you know if you see SiO2 or SiC, that's going to be your answer right away. So now let's move on to ionic bonding. Ionic bonds are formed when electrons are transferred from one atom to another, usually between a metal and a nonmetal. This transfer creates a positively and negatively charged ion that are strongly attracted to each other. And due to the difference in electronegativity, these strong electrostatic forces are going to require a lot of energy to break apart. And they're going to arrange themselves into a crystal lattice structure, which explains their rigidity and their high melting points. The particles in solid Ki, which is a stable ionic compound, are arranged to maximize Coulombic attractions while minimizing Coulombic repulsions. Which of the following diagrams best represents the structure of solid Ki? So we know that we want to minimize the amount of repulsions, and repulsions are going to happen between charges of the same type, which means negative and negative or positive and positive. So the answer for this one would be A, because each negative is surrounded by positive and each positive is surrounded by negative. So we're maximizing our attractions and we're minimizing our repulsions. Last unit, you were introduced to Coulomb's law, and remember, when we compare ionic bond strength, there are 2 key factors that I want you to look at. The first one is charge. Bond strength is directly proportional to the charge of the ions. The higher charges mean stronger attractions, kind of like a magnet. Secondly, you're going to be looking at ionic radius or size. Bond strength is inversely proportional to the size of the ions. So smaller ions can get closer together, so the attractions are stronger. When we put all of this together, we know that a stronger bond is going to mean a higher melting point because we have to put more energy in order to break those bonds. So let's do an example of that. Which ionic compound would have a higher melting point, lithium fluoride or sodium bromide? Now remember, whenever we're looking at the attractions between a positive cation and a negative anion, we need to first look at charge. Now lithium has 1 valence electron, which means when it becomes an ion, it's only going to lose 1 electron, which means it has a positive 1 charge. That is the same case with sodium. Sodium has one valence electron, so it's going to donate that to bromine and have a positive 1 charge. Now looking at fluorine. Fluorine has 7 valence electrons. It's going to accept that 1 valence electron from lithium and now have a negative 1 charge. And same with bromine. Bromine has 7 valence electrons. It's going to accept that 1 valence electron from sodium and now have a negative 1 charge. So you can see both of these two compounds have the same charge values, a positive 1 and a negative 1. So we're going to move on and look at the radius. Now the first thing you want to look at in terms of radius is the number of occupied energy levels. So lithium gave up its 1 valence electron in the second energy level. So it only has 1 energy level occupied, which means it's a really small ion. Then looking at sodium, sodium lost its 1 electron in the third energy level, so it only has 2 energy levels. However, that is more than lithium, so sodium ion is much larger than the lithium ion. Same with fluorine. Fluorine has only 2 energy levels, while bromine has 4 that are occupied. So fluorine is much smaller than bromine. So because of that, lithium fluoride is going to have a much higher melting point because the radius is smaller, which means the attraction between the two is going to be greater. Let's do another example. Which compound will have a higher melting point, MgF2 or NaF? So again, when we're looking at Coulomb's law, or the attraction between ions, we need to first compare the charges. Those are the most important. So when we look at magnesium compared to sodium, our two metals, magnesium has 2 valence electrons, so it's going to donate both of those and become a 2 positive charge, while sodium only has 1 valence electron and will form a positive 1 charge. So since magnesium has a greater charge, magnesium fluoride is going to have a higher melting point because the Coulomb attractions are way stronger in magnesium fluoride than in sodium fluoride. Which of the following compounds will have the most ionic bond character? When it's saying ionic bond character, it's essentially the extent to which a bond resembles a pure ionic bond, which is just going to be determined by electron transfer and attraction between oppositely charged ions. So the greater the electronegativity difference, the higher the ionic bond character. So let's look at our 5 options. Now we know that an ionic bond is going to occur between a metal and a nonmetal. So phosphorus and oxygen are both nonmetals, so those would have covalent bonds and not ionic bonds. Then we have carbon monoxide, which is also 2 nonmetals, which would be covalent bonding, so no ionic bond character there. And then E is also 2 nonmetals, so that would also not be considered in this question. So this is a past AP test question, and 3 of the options were immediately canceled out, and you're down to a 50-50 shot. So now let's compare our 2 ionic compounds, lithium fluoride and barium oxide. So I have circled the elements on the periodic table. Our lithium fluoride is circled in blue, and our barium oxide is circled in purple. Now you can see horizontally that lithium and fluorine are farther apart than oxygen and barium. And the reason I'm talking about horizontally is horizontally between atoms, the change in electronegativity is much greater than it is vertically. So when I'm looking at 2 ionic compounds, I like to look at them horizontally only because you do not have to know the actual values of these electronegativities of the elements. So this is just used so you can see the relationship between them all. But if you have a problem like this in the periodic table, you can just think of it as the horizontal distance and not really the vertical distance. So looking at lithium and fluorine, those are further away from each other, so we know the electronegativity difference is going to be greater, which means lithium fluoride will have the most ionic bond character between lithium fluoride and barium oxide. So we just learned about ionic bonding and how electrons are being transferred. Now we're going to move into covalent bonding where electrons are going to be shared. So there are two types of covalent bonds that you need to worry about, nonpolar bonds and polar bonds. So a polar covalent bond is formed when there is an unequal sharing of electrons, while a nonpolar covalent bond is going to be formed when there is an equal sharing of electrons. So when we're talking about these bonds between two different atoms, you need to look at the difference in electronegativity. And the bigger difference in electronegativity is going to tell you that it's a polar covalent bond. And if they are similar in electronegativity, it would be a nonpolar bond. So in terms of which bonds will form depending on the different electronegativities, if you have a difference of electronegativity that is greater than 1.7, that's going to be an ionic bond. Now that should make sense to you because the left side of the periodic table has much lower electronegativities than the right side of the periodic table, so there's a big gap between the two, and we know in an ionic bond it's between a metal and a nonmetal, which is the left side of the periodic table and the right side of the periodic table. Now when we're talking about electronegativity differences in covalent bonds, the actual number is if the difference is in between 0.4 and 1.7, that would be a polar covalent bond. If it's 0.4 or less, then that would be a nonpolar covalent bond. Something I need you to write down in your notes is that whenever you are looking at a bond between a carbon and a hydrogen, it is nonpolar. So it is about a 0.4 difference, and it is considered a nonpolar bond because the electrons are shared quite equally. Here is a larger version of the electronegativity values of elements. Again, you do not have to memorize these. I just like to show you so you can understand the trend of the electronegativities, especially that if you're going horizontally on the periodic table, you can see that the difference in electronegativities are pretty large, especially in that period 2. So fluorine starts at 4, it goes down by 0.5 each time. But then if you look at the difference between sulfur and polonium, so sulfur is here and polonium is here, it only goes down by 0.5 if you go down 4 elements. So the difference is much lower. So when we're looking on the periodic table without these actual values, just note that if you're looking at it horizontally, it's going to be a much bigger shift than vertically. All right, so we talked a few times about dipoles, and I want to specifically go over what a dipole is because it's really important when we go into Lewis structures, formal charge, so on and so forth. So a dipole happens when electrons aren't shared equally in a bond. So one side of the bond becomes a little negative and the other side of the bond becomes a little positive. So the best way that, in my opinion, to think about this is if you were playing tug of war. So think of a dipole like a game of tug of war. If both people pull with the same strength, the rope is going to stay in the middle. That is essentially a nonpolar bond. It's an equal sharing of electrons. Now, what happens if one of those people playing tug of war is extremely stronger than the other? That means that the rope is going to get pulled towards that stronger person, and that is an unequal sharing of electrons, which would be a polar bond. So that's the same concept when we're talking about atoms in a molecule. So let's take water, for example. The red is going to simulate an oxygen atom, and the whites are going to simulate a hydrogen atom. Now we know by looking at the periodic table, oxygen is much closer to fluorine, right? So we know that oxygen is more electronegative than hydrogen. Well, what does electronegative mean? Electronegativity means the ability to attract electrons. So what that means is that oxygen will have a partial negative charge, that is the symbol for partial, and your hydrogens will have a partial positive charge. Now, what does that mean? That means that oxygen is going to pull the electrons closer to itself, which is why you can see in this bond the shared electron from hydrogen is inching closer to the oxygen because it's pulling towards oxygen. So this is what a dipole is. When you have that unequal sharing of electrons, it creates this dipole of negative charge, which shows you where most of the electrons are housed. So let's do a practice question. The largest dipole moment will be seen in which of the following molecules? So if we are talking about a dipole moment, that means we need a polar molecule. A nonpolar molecule is not going to have a dipole because it's equal sharing of electrons. So let's look at our first option, CH4. So we have carbon in the middle. Carbon is in group 14, which means it has 4 valence electrons. So it wants 4 bonds. Now, conveniently enough, it has 4 terminal atoms, or 4 hydrogens. Hydrogen each has 1 valence electron. So the carbon and the hydrogen is going to share its electrons to form a bond. So as you can see, on this carbon are 4 hydrogens. All have the exact same electronegativity, which means they are all pulling at the exact same rate, which means this is a non-polar molecule. Next up, we have CH3OH. So whenever you have carbon, remember that goes right in the middle, right? And then we know carbon has 4 valence electrons, which means it wants to bond out 4 times. And we have 4 terminal groups. We have 3 hydrogens, which each have 1 valence electron. And then we have an hydroxyl group, which is an alcohol. So OH, that means we're going to have an O. We know an oxygen has 6 valence electrons. It's going to have 2 lone pairs and 2 electrons that wanted to be bonded out. And then we have our hydrogen on the end, which again we know has 1 valence electron. So now we can go ahead and form our bonds. And now you can see, if we're looking at this carbon in the middle, this oxygen is much more electronegative than the 3 hydrogens, which means this oxygen is going to pull the electrons in this direction of the molecule, which means this is a polar molecule. So this is definitely one of our contenders for this question. Next up, we have H2. H2 is a diatomic molecule, so we just have 2 hydrogens, each with 1 valence electron, so it's just going to form that single bond between the 2. This is an equal sharing of electrons, so this would be a non-polar molecule. Then we have HCl, so that's 1 hydrogen, 1 chlorine. We know chlorine has 7 valence electrons, so it's going to have 3 lone pairs and form 1 bond. And then our final contender would be HF, which is very similar to HCl. HF also has 7 valence electrons. It's going to form that 1 bond. Now we know that both of these are polar because chlorine and fluorine pull electrons much more strongly than hydrogen. That's because they're more electronegative. So now when we're looking at this problem, we've already crossed out CH4 and we've crossed out H2 because those are both nonpolar molecules. Now we need to figure out which of these 3 polar molecules will have the largest dipole. And when we want the largest dipole, we're looking at the greatest electronegativity. Now, whenever you see fluorine, you need to think, ding, 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 big electronegativity value. So since fluorine is the most electronegative on the periodic table, it's going to have the strongest pull of electrons out of these 3 polar molecules. So HF would be your answer. Now it says draw the partial charges for each drawn out bond. The line given is the bond. So when we're getting partial charges, again, you're just going to look at the atoms on each side of the bond, and you're going to write whether it's a partial negative or a partial positive. So first with A, we're looking at carbon and chlorine. Carbon has an electronegativity value of 2.5. Chlorine has an electronegativity value of 3. So it's a difference in 0.5. So it would be a polar bond. And because chlorine has a higher electronegativity value, it's going to have the partial negative charge, whereas carbon here will have the partial positive charge. Now with B, we have two carbons which have the same exact electronegativity, so these will not have partial charges. Then on C, we have carbon and nitrogen. Carbon has an electronegativity value of 2.5. Nitrogen has an electronegativity value of 3. So since nitrogen is more electronegative, that will have the partial negative charge. Carbon will have the partial positive charge. Then for D, we have carbon and iodine. Carbon has an electronegativity value of 2.5, and same with iodine. So since they have the same electronegativity values, they will be a nonpolar bond, which means they will not have partial positive or partial negative charges. Then E, we have carbon and fluorine. Carbon is 2.5, fluorine is 4. We know fluorine is the most electronegative, so if you ever see that, just assume it has the partial negative. So carbon would have the partial positive. And then finally for F, I told you in the other slide to write down that if you ever have carbon and hydrogen, just always assume it's going to be a nonpolar bond. So these are not going to have a partial positive or partial negative charge. All right, I hope this video was helpful. If you have any questions, please let me know. I hope you have a great day.